so much.
Yeah, thanks for inviting me. It's my pleasure to be here. So today I want to talk about the approximation algorithm for like two problems. Okay, so those are called the first problem is called correlation clustering. Then the second problem is called metric violation distance. So I'm gonna call correlation clustering CC and then this guy MBD. Okay, so there are like two different problems. I mean, kind of like different looking, but then yeah, my goal today is to kind of show that these two problems are kind of similar. And then yeah, we kind of give up two different looking algorithms. But then I want to show that okay, they are actually coming from the kind of like similar space, and then they are related. Okay, so that's yeah. So it's gonna be like two different algorithms, but then yeah, I want to emphasize that okay, so they are coming from the same space. Yeah, and then I'm gonna show you where they are coming from. Okay, so then yeah, let's first like start by defining those problems. Okay, so yeah, those are both optimization problems, discrete optimization problems. And then yeah, first one, correlation clustering is defined as follows. Okay, so the input is the complete graph G. Okay, so I'm gonna whenever I use E here, I'm gonna denote E by just like B choose 2, complete graph. But then yeah, each edge is either labeled plus or minus. Okay, so I'm gonna let the E plus to be the set of plus edges, and then E minus to be the set of minus edges, and then this is this means a disjoint union. Okay, so then yeah, that's a whole input. Okay, so they are complete graph, and then some edges are plus, some edges are minus. So then yeah, what we are trying to do is to cluster the whole vertices. Okay, so my output is supposed to be the partition or like clustering of the vertex set into like disjoint sets C1 through Ck. That whose union is V. Okay, that's very clear. But then what is our objective function? Okay, so my objective function is to minimize the number of plus edges inside the same part. So sorry, actually, I messed up the sign, so it's okay, so number of minus edges inside Ci, and plus number of plus edges that cross different parts of the clustering.
Minimize, right?
Yeah, we are trying to minimize. Okay, so yeah, that's more so the intended meaning of the input.
Given or you're allowed to pick any partition?
So second K
is given or you're
algorithm can choose K. That's a beautiful problem. Yeah. So it's kind of different from this like the more like a famous objective like K median, K means, yeah. So algorithm can choose K. Okay, so yeah, if you want, yeah, the algorithm can choose like all the vertices into one set. Of course, if you do this, then you're gonna pay for this part. You're gonna pay for every minus edge, and then yeah, if the algorithm can choose like algorithm can make every like vertex a single set. So then the algorithm gotta pay for every plus edge. Okay, so that's that's the problem. So then yeah, intended meaning is that yeah, so suppose that you are like you are trying to cluster these vertices, and then you rank some kind of classifier within each pair. And then some like human classifier like tells me, okay, so between I and J, I think that I and J must be in the same cluster. They're the same guy. Okay, so then the input becomes plus. And then sometimes like a human classifier will say, okay, so I think I and J might be in different clusters. Then the input is minus. And then our job is to find a clustering that is the most consistent with the observations that are given.
So basically, plus edge encourages you to put the two vertices in the same cluster,
exactly,
and minus encourages you to put them in different.
Yeah, exactly. So yeah, for example, if input looks like this, okay, suppose that input is already divided into like some clusters, and then suppose that everything inside is a plus, and then every crossing is minus. Then the objective function, yes, the optimal value is 0. You need to exactly output this cluster. Of course, but then there are like will be some noises. So you might see like some minus edges here, and then you might see some plus edges there. And then the goal is to minimize those like the errors.
Just for some intuition, what if you flip that? Like, is it obvious what you should do?
Yeah,
like
if you flip
minus
that, yeah.
inside and plus is between.
Yeah, then I think the kind of instance becomes like kind of completely bizarre. So I guess probably then you can't do much better than either like taking everybody together or just like making everybody separate. Yeah, that's my guess. Yeah, but then it depends on what sizes are. So yeah, is our correlation clustering problem clear? That's good. Yeah, and then okay, so the second problem is I call the metric violation distance. Okay, so yeah, it's kind of more like continuous flavor. Okay, so input is just the one vector from we choose to. So basically, yeah, we are giving some kind of distance between each pair I and j. That's good. Yeah, but then input doesn't have any like a requirement. Any vector will suffice. Okay, so and then what I want to do is that I want to fit x into a metric. Okay, so yeah, by metric I just mean kind of semi-metric. So I'm finding the 2 points at the same location. Okay, so all I want to satisfy is to make sure that the y, our output, satisfy the triangle inequality between every triple. Okay, so yj is at most yik plus ykj.
Input is not negative or
Yeah, I think of course it's not negative. Yeah, it's a negative. Then yeah, of course you gotta change that. Yeah, so yeah, we can add this.
It's just, the input could be negative and you can.
Yeah, let's say this. Yeah, but then yeah.
Okay.
Yeah, so then okay, so I want to find a metric y, and then all I want to do is to minimize this L0 distance, just like the number of entries, which is a different from between x and y. I want to minimize that guy. In other words, what I want to do is that okay, so I'm given some like distance, the pairwise distance, which is like supposed to be a distance, but then it might not be a metric. Okay, so then my goal is to modify the smallest number of entries of x to make sure that the modified the distance actually becomes a metric. Okay, so yeah, that's our second problem, metric violation distance. Okay, so yeah, is the problem clear as well? Oh yeah, those they're like those problems, and then we're gonna study them. But then you can kind of see kind of similarity between all these two problems. So yeah, you are given some kind of the distance data. Okay, so here the MBD is just like the completely arbitrary vector for correlation clustering. And you can think of it as like the 0-1 distance. Okay, so that one way to view correlation clustering as some kind of special case of MBD is that so you are trying to fit your metric into like uniform metric, by which I mean just the metric with the distance being only 0 or 1.
Oh, so you allow pseudo metrics as well.
Yeah, I think actually some of the like all the terms, but
You allow two different things to have distance 0.
I think that's exactly that. Yeah. So yeah, we
Distance
only
0 is if they lie in the same cluster.
Exactly. Distance 0, they're basically at the same point, and then 1 otherwise. Okay, so one way to view CC as an MBD is like you are trying to fit your like distance data into this like the 0-1 metric, and then even your distance is like 0-1. I think that's a one way to view CC as MBD. Okay, so in that case, those kind of related, and then that's why I presented these problems as a kind of metric embedding problem. But then the one reason I really like those problems is that they can be interpreted in so many languages. Okay, so one way to interpret them is to view them as a constraint satisfaction problem. Okay, so let me. Perhaps we're not gonna formally do it, so it's let me be kind of informal. But then one way to view those two problems is that suppose that in the CSV interpretation, interpret each of the vertex as a variable. Okay, so we are giving some label to each vertex, but then the label set for CSV corresponds to like some point in a general metric space. Okay, so if you want to be more specific, then one can assume that okay, so it has endpoints, and then perhaps if you look at the L infinity of n dimension, then it can represent every metric. Okay, so the variables is like the V vertices, and then perhaps like alphabet. Maybe just L infinity to the n or n minus 1, whatever space that can represent all the endpoints metric. Okay, so then our job is to assign the one point in the metric space to each variable. And then then if you look at the two variables I and j, so then after assigning those labels, then it naturally induces a distance between the I and j. And then we are checking whether like the distance we computed by giving labels is consistent with the constraint or like the data that we are given between I and j as input. If they are the same, then then we are the constraint between I and j is satisfied. If they are not satisfied, then the constraint between I and j is not violated. So then in that interpretation, then all we are trying to do is to minimize the number of the violated constraints. Okay, so it's so in that sense, it's just like CSP with in a complete graph. Okay, so which is kind of well-studied object. But then the one kind of difference between the literature is that if you are familiar with the dense CSP, then the people thought about dense CSP for a while, but then actually they talked about maximization version. Okay, so maximizing the number of satisfied constraints. Okay, so for those guys, there's like the p-test, the very good approximation. But then if you look at it's the same problem, but then if you look at the different objective function, minimizing the unsatisfied clauses. So that's kind of like the less studied. And then our problem can be viewed in this way. Okay, so we're not gonna explicitly use this, but then we're gonna draw like some ideas from this when we get to the algorithm. Okay, so so that's one interpretation. And then the other interpretation, which we will use like more explicitly, is again the heating cycle. It's more specifically heating the bad cycles. Okay, so so then here the interpretation we're gonna give is that suppose that let's look at the correlation clustering. And then suppose that I observe this cycle. There's a cycle, there are like a bunch of plus edges, and then there's like one minus edge. Okay, so then questions like, can I keep those like the labels unchanged? Is there a solution? Yeah, where like all these labels are unchanged. The answer is no. Because like there's like the plus edges mean that these two should be in the same cluster. These should be in the same cluster, these should be the same, these should be the same, but then there's a minus. Okay, so it's a contradiction, which means that so if this is a fine input, but then after like do like pure clustering, the true clustering, then at least one of these edges should change the label. That's all very naive observation. Okay, so then it means that so for every such a bad cycle, we gotta like change at least the label of one edge. And then that's the same for MBD. Okay, so then even for MBD, let's draw the same cycle. But then suppose that it's a 1, 1, 1, 1, 7. Okay, so then we know that so then if this is a fine X as an input, but then in order in Y, of course this is not valid metric. Okay, so then and then from this cycle we need to change the distance over at least one edge in the cycle. Okay, so then this interpretation that so those are called the bad cycles. And then the one kind of actually equivalent interpretation of both problems is that find smallest say solution E, which is like subset of edges that hits, which also means intercepts every bad cycle. Okay, so that's our second interpretation of this problem. Okay, so now like choose like subset of edges. That's gonna hit every bad cycle in this way.
Just to understand, like if you flipped each of these things, you might create new bad cycles, right?
Yeah, is it clear that you could just flip one by one and
Good. Yeah, that's a very valid question. That's okay. Let's see in the correlation clustering. Okay, so suppose that so then so when once you choose like heating set S, So then let's just like delete this edge.
And wait,
But
deleting? Or-
So after choosing S, and then then I'm gonna delete those edges. So there are like three types of pairs: plus, minus, nothing. And then I want to claim that there exists there is a way to assign the labels to like nothing, so that it becomes a perfect clustering.
I guess because you just say, well, this is gonna kill it. This is gonna be accounted on the objective.
So exactly. So we remove these guys for a while. And then we look at
The number of edges we moved.
Then we look at the rest of the graph. There has like there's like each pair is like a plus, minus, or nothing. But then we look at the connected components of induced by the plus edges. Okay, so then okay, so this is one connected component. But then one thing I know is that if you look at the one connected component here, the plus edges, there shouldn't be any minus edge inside this connected component, because I already hit all the bad cycles and then remove them. Okay, so there might be some nothing pairs.
But heavily, but okay, you're looking at it. Yeah, sure, it's not connected.
So then I'll say like, okay, so this is my cluster. And then so that's the clustering. Then one can see that at least this one pair is not deleted by S. So then it's going to be totally satisfied in the clustering. Okay, so that's kind of tricky. Thanks for the question. It's highly non-trivial. And then it's kind of the similar thing happening here. So then what you're doing is that, okay, so you choose like set of edges that at least hit all the bad cycles. Then okay, so I'm gonna delete some of the edges. Okay, so then it's nothing but just a weighted graph, not necessarily complete. But at least you know that, okay, so in this case there's like no obvious contradiction. Then you can just complete it this metric by the shortest path metric. And then one can kind of see that, okay, so resulting guy will be consistent with every undeleted distances. And then we're going to get the desired approximation. Good. Yeah, so those two are kind of different interpretations of this problem. The metric problem, and then we are going to like use kind of some aspects of both interpretations to give an algorithm. Cool. Okay, so that's so that's the problem. But then let me try to say a few words about what we're gonna do, or like what was known. Okay, so correlation clustering. This guy had some kind of a rich history. So I mean not very long, but then I think the correlation clustering is first defined by this paper by Blum, and Chala. I think it's like 2001, 2002. Okay, so they first defined this problem, and then they give like constant factor approximation, where the constant is quite large. Okay, so let's just like say order 1. And then there are like several people improving this constant. But then the paper that we're gonna really look at is the paper by Island, Troika, Newman. I think the conference version was like 2005. Okay, so they gave 2.5 approximation. Actually, I'm going to talk about this paper later as well. So 2.5 approximation, and then 10 years later, this paper by Chala, Makaricek, Shiram, and Yaroslavtsev. Okay, so it's a 15. They slightly improved the constant, 2.06. Okay, and then
correctly, this constant is basically minimizing this number of edges minus plus edges plus, and this is relative to the optimal.
Exactly. Yeah.
But also, you mean like this is a polynomial algorithm?
Yeah. Whenever I say approximation algorithm, I imply that it's
so I presume that the 206 is slower than the 2.5 or not?
Yeah, essentially, those two algorithms are like very the running time is almost the same. I'm going to tell you why they do different, what they do differently than this. But then yeah, those two are very similar. The running times are going to be the same. Okay, so but then actually that's a very good question because like yeah, when I present my result, actually running time is okay. Yeah, the valid concern. Okay, so then yeah, our glorious result, which is done by with Vincent Coinadad and Alan Newman. Okay, so then yeah, we slightly improve this constant 2.06 to 1.994 plus epsilon. Okay, so yeah, and then the running time is gonna be n to the order 1 over epsilon squared. Okay, so I think yeah, here it's a purely polynomial time, perhaps like the n cube time. Correct, sorry?
For any epsilon.
For any epsilon, yes, yeah, for any epsilon. Okay, so yeah, yeah, so it's yeah, so if you set epsilon to be like 1 over a million, then it's yeah, it's almost 1.99 for approximation with the tail running time. Yeah, so yeah, okay, so you might ask, okay, what's a big deal about this? Okay, so and then yeah, when it's yeah, first it might not be a big deal, but then yeah, my kind of claim is that 2, yeah, the number we kind of broke was like thought as like some kind of barrier. So yeah, for one line answer is that it is like the standard LP, the integral gap with the standard LP relaxation. And then all the previous algorithms were based on this like LP relaxation. Okay, so we kind of gave a new the algorithm or new kind of framework to go beyond 2. Okay, so that's yeah, one selling point of this problem. Okay, so that's
By the way, is this problem known to be like NPC or something?
Oh yeah, exactly. So okay, good. So yeah, it's definitely NP complete. And then it's already known that yeah, you can't arbitrarily well approximate this problem. So it's called the EPX hardness. So I think yeah, so yeah, yeah, I don't exactly
think exists a polynomial
yeah
time algorithm that solves it precisely.
Yeah, so I think yeah, so perhaps like if you yeah yeah, if you really work hard, then yeah, you can show that there's the 1.001 approximation is ruled out. If you get below this, then p is equal to n. So that yeah, that's I think it's from Charlie Clark, Goswami work. Okay, so yeah. Okay, so this is all I state of art, and this is what we did.
Is the 1.994 anything actual?
No, I think actually, yeah.
It's just whatever pops up.
Yeah, I think, yeah. I mean, actually, I'm going to tell you a bit about, yeah. Just, yeah. Okay, so yeah, that's a history for correlation clustering. And then again, let me tell you a bit more about this problem. I think, okay, so yeah, this problem, yeah, so it's a well-defined theoretical computer science problem, but then somehow this problem got picked up by not practitioners, yeah, practitioners, yeah, I think people outside like math and computer theory. I think the original paper is like cited like more than 2,000 times, which is impossible if you just like work for like theoreticians or mathematicians. And then yeah, my one other like anecdote is that I did only one work. I had only one job outside theory in my life. So I had an internship right before my PhD at some company as a software engineer. But then yeah, when as soon as I got there, they kind of saw me through. Okay, this guy doesn't know anything about the algorithm. So what they wanted me to do was to look at actually exactly correlation clustering algorithm they implemented, and then yeah, they wanted me to like fix that. Okay, so yeah, this this correlation.
They want you to what?
They were like solving correlation clustering problem, and then yeah, they wanted me to improve their algorithm. Okay, so yeah, this is something that is implemented.
So it sounds to me like you improved it.
Yeah, after 10 years, yeah, after 10 years. But it's like crazy running time. Yeah, I should go back to my manager and say, okay, give me a job. Yeah, so yeah, that's yeah. So this is a kind of problem well studied even outside theory. And then yeah, MVD is like the shorter history. So let me just write it here. Okay, so yeah, we Google this, and then this problem I think was studied in different communities like computational biology more heuristically. Yeah, but then within like theory community, I think the first the paper that actually studied this objective function is this paper by Van, Rachel, and Van Busberg. And then yeah, so they got the approximation ratio, which is opt to the 1/3.
Sorry, I can't see what's.
Okay, sorry. Okay, so that's their approximation ratio. Okay, so opt is just number of the optimal value of the problem, which can be as large as n squared. Okay, so this is so this is like still like polynomial approximation ratio. So the problem is kind of new. So it is the first the non-trivial algorithm was published in 2018, and then our result kind of improved this. So it's a different paper, still
I'm speaking about MVD.
Sorry,
I'm speaking about MVD.
yes, MVD. Okay, so for that, Fan and myself and Leslie. Okay, so again, then the approximation ratio we got for this problem is order log n, which is kind of an exponential improvement over this opt to the 1/3 approximation.
So up to the 1/3 is the ratio, right? So the up to the 4/3.
Yeah, exactly.
I was a bit
Slowly opt. So that's the result.
What's the order of magnitude of the optimum?
Opt, you can't control. It can be as large as like root 10 or like whatever. So that's just their guarantee. If opt is a constant, probably their algorithm works better. Okay, so that's that's the approximation ratio we got. Okay, good. So that's that's our result. Pretty nice. Okay, good. But then, of course, so we have the two algorithms. I'm gonna tell you what these algorithms are and how to analyze them. But then, as I said, okay, so those two algorithms actually are kind of coming from kind of the same place. Okay, so which is essentially coming from this the brilliant idea of island tracker neuron.
So can I ask, what is n here? Is it the number of vertices?
That's Good. Okay, so then so the both algorithms are coming from their like framework. Okay, so then let me briefly draw the picture of what they did in this work. Okay, so then if you look at this result by Island, Turk, and Newman. Okay, so their papers they only studied the correlation clustering problem. And then they keep this like the beautiful the algorithm called the pivot algorithm. Okay, so so I present it's not exactly one algorithm. It's more like the framework to design algorithms. And then using this like the pivot framework. So then there are like several ways to implement it. So then the first way to implement it is you can combine it this like paradigm with the LP relaxation. And then using that, they gave a 2.5 approximation. Okay, so that's 2.5 right there. But then with this like the framework, you don't even need to solve LP. So then with this paradigm, they gave a purely combinatorial algorithm. Though the analysis kind of goes through some kind of LP framework, but then the algorithm itself is like purely combinatorial. Okay, so using combinatorial algorithm, they got like 2 approximations. And then this guy was like what was implemented at the company that I was working. So very nice algorithm, and then we're going to see both of them. And then our 2 algorithms actually come from these like 2 different branches. So then what we're going to do is that so correlated constraint, of course we're going to improve it, and then we're going to take this the LP rounding approach, and then strengthening with more powerful LP relaxation called the Sherali-Adams hierarchy. And then we're gonna that's gonna be 1.994 approximation for like correlation clustering. And then what we're gonna do for MVD is that I'm gonna take this combinatorial algorithm, and then of course it's a more general problem, but then I'm gonna like modify it in a very natural way, and then show that actually it gives us the log n approximation algorithm. Okay, so that's our plan. Okay, so So there's a pivot framework, and then it leads to like two kind of different algorithms for correlation clustering. But then you're gonna kind of modify them to get the algorithm for MPD, and then kind of strengthen them to get our algorithm for correlation clustering. Cool. Any questions? Okay, good. Yeah, then of course then I gotta tell you what this the pivot framework is. Okay, so let's yeah. Okay, so again, yeah, those are for like correlation clustering. Okay, so the pivot algorithm. Okay, so then yeah, it's a very like natural algorithm. Okay, so yeah, recall that in correlation clustering. Okay, so we are just given graph with the plus edges and minus edges, and then our job is to partition, get a cluster, partition the vertex set into like clusters. Okay, so then what they're doing is very like natural iterative algorithm. Okay, so yeah, what they're doing is okay, so then each iteration we're gonna like choose one set from the current vertex set, make it one cluster, and then recurse with the rest of the graph. That's what they're doing. It's a very iterative algorithm. Of course, then yeah, we gotta see what we gotta determine is that in each iteration, so how we're gonna choose like this set that will become one cluster. Okay, so then yeah, again they do like very natural. Okay, so suppose that we start from the initial graph, and then if something remains, then yeah, we just run the algorithm. And then the way they take out the cluster is starting by choosing a uniformly chosen pivot vertex P from the remaining vertex. So the uniformly. Okay, so like this, like the P is kind of like the seed that will determine the whole the cluster. And then yeah, we're gonna decide, okay, so given P, then how are we gonna choose S? Okay, so then yeah, okay, so choose so S somehow. Let me be vague about this. Yeah, but then then algorithm. Okay, so S is one cluster, and then the V. That's the whole algorithm. Okay, so very simple. But then of course I was kind of vague about how to choose like this set as containing P. And then yeah, then that's where these like two the algorithm differ.
So just to make sure I understand, so you choose this cluster solely based on whatever is remaining in V. And you don't unite it to anything that you already took out.
Yeah,
and you will never unite it with anything that you did not choose it at this iteration, right?
Exactly. That's a beauty of the algorithm. It's like totally oblivious like to this iteration. Yeah. Okay, so actually okay, so then yeah, basically yeah, then we choose P. We know that P is gonna go. Then yeah, then by doing this, we are basically deciding who's gonna go with P. That's the decision we're gonna make. Actually, so I forgot to to write down the L2 relaxation. But then let's at least like state on the combinatorial algorithm. Okay, so any guess for like how in the combinatorial way you don't have any information, just like the only thing you have is the graph, the input graph with some plus and minus edges. Then can you guess like who should go with P?
Well, probably you insinuate those that have plus sign inside V, right?
Yeah, exactly.
The neighbors are the component. One of those.
I think
but probably there's going to be some surprise.
Yeah, I think you're exactly right. So the in combinatorial through approximation algorithm. Okay, so combinatorial algorithm. So then the S is exactly the set of plus neighbors of P.
You ignore all the edges between whatever remains in V.
That's a crazy part.
The other.
Yeah, that's a crazy part. Yeah, it might be the case that all the plus neighbors of P have all the minus edges. It might happen. So then if that happens, then like it's a really bad cluster.
Yeah.
But then regardless, we're gonna show that this is a through approximation. Okay. Yeah. So that's all. Yeah, that's a very bold strategy. admittedly, though I think that yeah, we're gonna see.
So I didn't quite understand this pivot thing. Is it the new ingredient that you have, or was it existent in this?
Oh, I think yeah. So there, yeah. So everything I'm gonna say for like the 10 or 20 minutes from now, I think it's from the ACN paper.
Okay.
Okay, so that's something that's a very bold algorithm.
Just a greedy algorithm. The only thing is that you're using randomness here.
Yeah. And then yeah, it's really bold. Like I mean, perhaps like some you might want to look at some density, and then but then just like don't look at anything. Just like take all your cross neighbors without worrying about their relationships. It's pretty bold.
By the way, is this ratio, is that the expected ratio, or is it the worst scenario?
Yeah, I think So I'm going to present them as like randomized algorithm. Then it's an expected ratio. Though I think the standard argument, the conditional expectation, things like that. Yeah, it's one can make them deterministic approximation. Okay, good. So I told you combinatorial tree approximation algorithm. But then in order to define what LP algorithm is, I gotta tell you what LP is. Okay, so perhaps like this LP might be inspired by this like the CSP view in some sense.
What does the LP stand for?
Linear program. Okay, so then what are we trying to do? Is that okay? So then we are trying to cluster these vertices. Yeah, and then of course in our like CSP interpretation, so the alphabet is like any point in the metric space. So I can't just like have a variable for each of the variable label pair. But then what I can do is at least so given two vertices, I can query, okay, so what's their distance in the metric? Okay, so then so the inspired by this, so then I'm going to design LP whose variables are xij, or like ij is just any pair. And then okay, so then at least then our intended meaning is that xij is supposed to be a distance between I and j, and then we are still in the correlation cluster problem. Okay, so then ideally we want that xij should be 0, meaning that okay, ij are in the same cluster or like the 1, ij are in the different cluster. Okay, of course we can't infer this. We're gonna leave it the xij perhaps like between 0 and 1. But then with that interpretation, then what's gonna be the objective function? Okay, so then probably objective function. Okay, so then if you look at the one edge ij, then it kind of depends on what the label of this ij is. Okay, so if it is a plus edge, then I want xij to be 0. Okay, because that's and then if ij is like minus edge, then I want xij to be 1 because I want ij to be different. Okay, so then the very natural objective function I can write is summing over all plus edges xij, and then sum over all the minus edges 1 minus xij. Okay, so if you are plus, but the xij is 1, then we're gonna pay 1. If xij is the ij is a minus, if you're like 0, then you're gonna pay 1. Okay, so that's some very natural objective function to write. And then then what kind of constraint can you imagine? Okay, so perhaps one can say that okay, x better be between 0 and 1. That's for sure. But then as we said, we want to enforce that xij is like this uniform metric, 0, 1 distance metric. But then we can't do this. But then at least one can ensure that xij forms the metric or like pseudo metric. Okay, so then what I can do is I can write down this triangle inequality constraint within every triple. So for every ijk, I can demand that okay, so xij plus xjk is at least xi. Okay, so that's my entire LP relaxation for this problem. Okay, so this is clear. So it's a relaxation for the problem. Okay, so then with that LP relaxation in mind, let's go back to this algorithm and then see what should be the rounding algorithm based on the LP values. So now suppose that we are doing the same thing, but then we initially solve this LP relaxation in the beginning, and then we're going to solve it only once. It's solved only once, and then we keep this we have this value xij for every pair ij. So then given this pivot p, what's gonna be the most natural choice to construct S given P using the LP values?
I guess the value 0, 1.
Yeah, I think so if it's a 0, 1, then decision is like trivial. So if it's a 0, 0, then they go with P.
Less than 1/2. 1.
That's very good. So, and then that's actually what some of the previous algorithms do. But then again, we are trying to be very reckless, very bold, very stupid. And then I want to use randomization. Okay, so then what should I do? Okay, so then probably the most naive thing you can imagine.
Maybe random with probability which equals to the value.
Exactly, yeah. So for then so definitely the P goes to S for sure. But then for each other vertex, what we're gonna do is that add U to S with probability 1 minus X.
Yeah.
Because XPU indicates whether they're different or the same. Okay, so and then crucial thing is it's again we're being very stupid, independent. That's the whole algorithm. Again, it doesn't look at anything about the edges between the other vertices. We are only making decision based on the P and its LP values. Very reckless algorithm. Still, it's does something. Please list the algorithms are. I state the algorithm. Okay, good. Everything's fine. The algorithms are okay, good. That's kind of the preamble of this talk. I told you at least the common roots of these two algorithms, and then now we have two parts. Okay, so then as you said, we can try to analyze the LP to by approximation algorithm, and then see how we can strengthen that to get a better algorithm, or you can just we can start from the combinatorial one, and then get log n approximation. Do you guys any preference about what you want to hear first? It's like PCP. I claim that I know something, and then you got to tell me
Hopefully we can expect more than just constant mathematics.
Okay, so then if you don't any preference, then actually let's do the LP version first. The correlation clustering is the same problem. Okay, so then then that's good. That's the LP, and then that's the algorithm. Then I gotta tell you how to analyze this algorithm. I gotta tell you why I choose a 2.5 approximation. Okay, so then it's a very complicated random process. It's an iterative, then each iteration we choose pivot randomly, and then after choosing pivot we do make every decision independently. It's a kind of very mess. But then of course the idea is kind of decompose this whole process into iterations, pivots, and pairs. Okay, so that after and to the point that at the end we're gonna only look at 6 numbers. That's the plan. Okay, so then let's try to see. So it's kind of a potential argument. One can interpret that way. Okay, so suppose that in the beginning of the algorithm. Okay, so then we look at the initial graph. Okay, so then nothing is violated. We haven't made any decision. And then we take 0 so far. And but then if you look at the whole instance, so then the LP we ran the LP relaxation. We got the optimal solution. So then whole instance contains some LP value. I mean, basically each edge is paying something to the objective function of the LP. Okay, so we in the beginning we pay our cost is 0 so far, and then our instance contains like some LP value. But then as we proceed, what's gonna happen is that we're gonna make decisions. We're gonna take some set, and then we're gonna take that as a separate cluster. By doing that, then we might violate some edges. Okay, so for example, if this was the whole graph, but then if we separate S out of the initial B here, so then the edges that we're gonna violate by making that decision is a minus edges inside S, and the plus edges outside the crossing S. Okay, so there might be some the edges inside induced by the rest of the graph. We still don't know. We might violate them or not. But at least like those two type of edges, minus edges inside the new cluster, or like the plus edges crossing the new cluster. Those guys we know that they're surely violated. So then we're gonna pay something. Okay, so then one can see that for each violated edge at the end, then there's like clearly one iteration that is responsible for that violation. Okay, so that's one observation. So the cost that we are paying will grow as we proceed for sure, and then it's gonna be the total cost when we end. But then if you on the other hand, if you look at the LP value contained in the current instance, then that's gonna shrink. Okay, it's the LP value that we're looking at. It's like simply the summation of the LP contributions of the edges inside our like current vertex set. Because that guy definitely will shrink. Okay, so then what you're gonna look at is that, okay, so let's look at one iteration. Okay, so in one iteration. Okay, so then let me define this quantity cost. Okay, so the cost is the increase or the number of edges the violated in this iteration. Okay, so number of edges like newly violated in this iteration. Okay, so we're gonna make some decisions, and then we're gonna violate some new edges that post the number of them. Okay, so then and then I'm gonna define another quantity LP. Okay, so LP is the amount of the total LP value that will decrease by going to the next iteration. Okay, so the amount of decrease in total LP value. Which is nothing but summation over all the edges incident on S, because like S is the set that we are choosing here. Okay, so it can be contained in S, or like it can process the summation over all the edges, its contribution to the contribution over E to this objective function.
So you do not rerun the LP in the other iteration?
Yeah, so we run LP only once in the beginning.
Oh, only once. Okay,
Yeah.
so it's
So it's very simple. Yeah.
I was thinking that you were going to.
No, we are. It's again, we're not. Algorithm is crazy, but the else is not crazy. Yeah. So it's just like everything is like determined in the beginning, and we're just like looking at how many things we contain. Very simple. Okay. So then so for one fixed iteration, I define as like cost and LP. Okay, so then both are like random variables, because like we choose like P for random, we choose like S random. But then what we want to claim is that, okay, so then if you look at the expected value of the cost, then we want to say that this guy is at most 2.5 times the expected value of the LP. Then I claim that if that is true for every iteration, then we're going to be done. Because we kind of our initial potential is like total LP value, and then in each iteration cost is increasing, and then the LP is decreasing. But then we are basically proving that if you are increasing your cost by something, then the potential will decrease a lot. And then of course, if you look at all the iterations, then total cost is a summation of all the cost of the iterations, and then LP, some of the LP value can be at most the initial LP value. Okay, so that's why then it suffices to look at prove like this inequality for like one fixed iteration. Is it good? Okay, so then that's nice. Okay, so then of course then we can kind of forget about the iterations. That's good. But then of course there's still like one this expected value of cost, expected value LP. I think it's kind of like still complicated because like you choose like pivot random, you choose like S random, things like this. But then let's decompose them a little bit more. Okay, so now like we can let's like totally focus on one iteration. And then I'm gonna define some quantities. Okay, so like I'm gonna define something like cost sub P of UV. Okay, so that's gonna be defined as like exactly the probability that UV is violated, given that P is P. Okay, so that's my definition of cost sub P of UV. Okay, let's do some see what this is actually. Suppose that we have this configuration. It's like P. We know that P is pivot, and then suppose that UV is a plus edge, and then this value is XPU, XP. Then can you tell me what the cost sub P UV should be? Okay, so then
XPU times 1 minus XPV was the opposite.
Yeah, exactly. So yeah, very fast. Yeah, basically what Leonardo was saying. Right?
The probability you pick one but not.
Yeah, probably. So this edge will be violated for sure if we include exactly one guy to go with P. And then if that's the case, then this plus edge will be violated for sure. Okay, so if both of them are included, then UV is not violated for sure. And then if both are not included, then its decision is deferred to the next round. Okay, so that's when UV is a plus edge. And then if it's a minus edge. Okay, so then I guess the only way that it's violated is when the U and V both go with P. Okay, so then it's gonna be 1 minus XPU, 1 minus XPV. Okay, so when UV is okay, so very simple plot. Okay. So that's good. So then then exactly we define this quantity. But then let's do the similar thing for LP. So it's slightly different, but then almost same. Okay, so then I'm gonna define LP. Okay, that's a terrible choice. LP sub P UV as the probability that UV is removed after this instance, which means that UV is an incident on S times the UV's contribution to LP. Okay, so the probability that UV is removed times how much it was paid for the objective function. So then that's the same game. And suppose that it's a plus edge. And then suppose so
Probability is removed. It's independent on whether it's a plus.
exactly.
You have to pick at least one.
So then this guy. Okay, so what is the probability that UV is removed? Okay, so so UV will be removed from the current instance, but like if the U or V or both go with P. Okay, so then probably is UV is removed is the 1 minus the probability that both are not there. So probably XPU times XP. Okay, so yeah, that's common whether like the UV is a plus or minus. And then yeah, and then of course if a UV is a plus, then it was like paying X UV to the objective function. And then yeah, it's probably the same. 1 minus X UV when UV is minus H. Okay, so that's that's the LP sub P of UV. Okay, so how much of the potential decrease we expect from UV when we know that P is chosen as P? Okay, good. Okay, so then very close to decomposing everything into 6 numbers or 3 numbers. Okay, so then still in the one iteration, we define cost and LP, but then we define those like those little guys. So then one can see that, okay, what is cost? Then cost is nothing but, okay, so we choose like the pivot randomly. And then we are just like summing over all the edges. Okay, so P and then UV. And the same for delta. So it's nothing happened, just like everything's over the expected choice of a pivot, and then we are just summing over all the edges. You see what's the expected total cost in that iteration? What's the expected LP value decrease in that iteration? Okay, so there, which is really nice. Okay, then okay, so I don't even like this like the different signs, expectation summation. So let me just okay, so it's the 1 over n times okay, so the PU, basically we are choosing like 3 versus PUV, but then like there's like slight nuance because like the P's are still in any vertex, and then plus like UV is the random any pair. Okay, so okay, so we broke down this like the complex quantity into like summation of like bunch of like n cube little quantities. Okay, so then you're very tempted to do this like the term by term analysis. Yeah, we would have been very happy if for each term like cost of PUV, LP sub PUV, if we were to have that cost of PUV is like at most 2.5 times LP sub PUV, then we would have been done. But then sadly it's not going to be true. Okay, so if you just look at them edge by edge, then there are like some
average over P.
Sorry?
Even if your average over P is not true.
Oh, okay.
If you fix an edge and average over P, is it not?
That's a good question. I guess might be yes, but then I'm not.
That's what I do at least.
No, I think no. I think So because like you look at this like No, it's a very So let's decompose like this like n cube things into like collection of n things, collection of like 2 things, collection of 1 thing, whatever. But then actually the their kind of innovation is to look at perhaps I get 1 by 1. That's not going to work. But then what they do is let's this is an inherent asymmetry here because like we are talking about 3 vertices, but then 1 guy's pivot, they did 2 guys from an edge. So then what they say is okay. So but then let's look at the triangle by triangle analysis. Okay, so then what they did is the cost of UVW. Let's define it as just cost sub U over VW. The cost of sub U VW B UW plus cost of W U. Basically, kind of the symmetrized like triangle, and then LP UVW is defined as similarity. Okay, so then I kind of amortize this thing. And then of course, I mean, there's like some kind of nuance here because like the P can be like equal to U or V.
And you need to just probably define it.
Yeah. You don't need to worry about that. Just something like. Something like this. Okay, so then we kind of group these like terms into like triangles and then this like kind of degenerate triangles or whatever. Okay, so then given this, okay, so then one can write down this thing. So let's see. Perhaps I'm gonna be off by some constant. But then the UVW, say like form a full triangle. Plus something like this, right? Because I might miss out, perhaps they need to go with a different factor. Is it? Okay. No, probably not. Yeah,
It looks okay.
yeah, looks okay actually. And then one can write down the same expression for LP. Everything the same except host becomes LP. Okay, so then now we are ready to do this like term by term analysis. So then the claim is that for any like triangle UVW, so the cost of UVW is at most the 2.5 times the LP of UV. So that's a claim they proved. Then how do we prove this claim? Okay, so I don't have a very good intuition about it. But then one thing I can say is that now we do this like term by term analysis. So then the only thing that we need to worry about in order to prove this claim is like one triangle UVW. And then the only information that we need in order to determine this is the signs of like these three edges, plus or minus. So that they're like three binary variables. And then the LP values, X values between those like three variables. Okay, so basically, so determine by signs and X value over those like three edges. Okay, so that's why I kept saying that everything will be reduced to like 6 variables. The signs of 3 guys and the LP values for 3 guys. Okay, so then I mean, it's still kind of tedious thing. I mean, we kind of suffer from that. They seem to suffer from that. But then it's not a terrible thing. You can prove based on this definition of cost POV, LP POV, just like some quadratic inequality in 3 variables. And then you have A cases depending on the things. Okay, so it can be drawn. Okay, good. Yeah, so that's how they prove the 2.5 approximation. And then let me say word about this like 2.06 approximation. Okay, so then what they did is actually that almost things are almost the same. They use the same framework, even the analysis framework. But then the project, the only thing they differ is to how to choose a probability. Even independence is the same. But then is that instead of naively looking at this probability, I mean, which is kind of a reasonable thing, but then you might want to try different probabilities. Okay, so then they just like kind of carefully chose like this the probability function that got this X value, and then output the probability you gotta use. Okay, and then they also like took signs of the edge into consideration, which the original paper didn't do. Okay, so they apply some function It's the LP value, considering signs. Still, yeah, but that's still everything the same. Decisions are made independent. And then yeah, that's and then yeah, you do the same analysis.
It's still independent for each other.
Yes, yeah, it's still independent. So yeah, everything will be the same until this point, which I didn't show. So then yeah, if you choose like F carefully, then actually it's gonna this 2.5 is gonna go down to 2.06. Okay, so that's good. Okay, so then yeah, okay, but then one question one might ask is that okay, so then it's like is a 2.5 tight? Okay, so yeah, if you just like look at the original rounding algorithm and this the lemma, then yeah, 2.5 is gonna be tight. Yeah, I'm gonna show you an example for a bit. Yeah, but then perhaps like the bigger question is that okay, so then we are basically proving this our expected cost in terms of the LP value. We proved that our like the cost of the solution is like at most 2.5 times the LP value, where we still use a standard relaxation. But then the question is, can we go like below 2 using this LP? And then the actual answer is no. I think there's an instance where like the LP integral gap is at least 2. Okay, so it's a very simple instance where we have like there's a star graph. If you just look at the plus edges. Okay, so there's like the star graph. Okay, so undrawn edges are just minus edges. And then the LP solution is going to be the half from every edge from the center to the other vertices, and then 1 everywhere else. Okay, so those are only like only those are plus edges. Okay, so then if you look at this graph, then one can see that okay, so if there are like the n vertices other than the root, so then the LP is paying n over 2. But then if you think about okay, so how to make the clustering integrally, so then perhaps like 2 possibilities that if you make everything singleton, then you're gonna pay n. And then perhaps like if you wanna include the center with 1 more guy, okay, so then we are saving this edge, but then the other I think this one is like paying n minus 1. If you put those 2 guys together and then make other guys singleton. And then you're kind of you're more adventurous. Then what happens if I put like 3 guys together? So then you are saving like 2 plus edges, but then you are like paying 1 minus edge. And then one can see that if you like include more and more guys there, then you're kind of linearly saving plus edges. And after that you're paying quadratically for the minus edges. So I think including 1 or 2 guys with the center is the best thing you can do. So the optimal value is like n minus 1 at least. That's kind of easy to show. Okay, so then in this example, the LP value was n over 2, and then the optimal value is n minus 1. Okay, so that's why the integrality gap tends to 2 when we just look at the LP relaxation.
I think if you include 2 guys, it's already 2n minus 2.
It
doesn't matter. It doesn't matter.
Okay, good. Okay, so so that's why the 2 was considered as like some kind of barrier. Because like as you see, like all these like previous approximation algorithms kind of based on this relaxation, and then that's gap of 2. Okay, so then I finally gotta tell you okay what we did differently. So then in order to do so, then I gotta tell you what is our relaxation anyway. Because like definitely then we need to use a different relaxation rather than this like the standard one. Okay, good. So then new relaxation. Okay, so we gonna call it the Sherali-Adams relaxation. Definitely it's inspired by Sherali-Adams relaxation for like CSPs. But then somebody told me that it's not exactly the formal strengthening, formal Sherali-Adams relaxation on top of this standard SCP. We believe that they're like kind of close, but then Yeah, I'm gonna present ours anyway, and then you're gonna see kind of similarity and differences. Okay, so then yeah, then what we're gonna do. Okay, so let me just like tell you what my variables are. Okay, so then what I'm gonna do. Okay, so then yeah, so I'm gonna make a variable for each collection of sets. Okay, so then suppose that S1 through SL is like the one collection of sets. And then yeah, and then I'm gonna make a variable called y sub S1 bar, S2 bar, dot 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 bar SL for those like collection of L sets. Yeah, but then yeah, my requirement, he said, yeah, they gotta be this string. Okay, so this string. And then yeah, and then I want to demand that I want to control the number of variables. So then yeah, I'm demanding that union size. Okay, so the size of their union is at most some constant R that we're gonna choose. Okay, and then yeah, and then eventually we're gonna choose R as 1 over epsilon squared. That's where this 1 over epsilon squared running time is coming from. Because if I do this, so then yeah, one can see that the number of variables is gonna be n to the 1 over epsilon squared. Okay, so yeah, okay, it's clear. Yeah, so it's well-defined variables. But then of course, yeah, before writing down constraints, then yeah, what is my intended meaning for these variables? Okay, so then yeah, my intended meaning is the following. Yeah, suppose that this is for instance V. And then let's look at this set S, which is supposed to be the union of S1 to SL. Actually, and then another fact is that L is not fixed. Because L can be any number. So there can be Y of a single set, there can be Y of like S bar T, things like this. As long as their union size is bounded. Okay, so then yeah, what is my intended meaning? Okay, so then yeah, the V is like the entire graph. And then yeah, S is some set of verses. So then yeah, then of course, so there's like some optimal solution. Okay, so that partitions are graph like this. Okay, so then yeah, okay, so the partitions V, that's fine. But then if you look at S, so then yeah, this like the optimal solution, partitions S as well. So then yeah, then I'm gonna look at, okay, so then what I want from those variables is that, okay, so tell me how optimal solution partitions like those like the set S that I'm looking at. Okay, so yeah, if this like the thing is an optimal solution, then we know that optimal solution partition density S into 4 parts. S1, S2, S3, and S4. And then yeah, if that happens, then I want that the Y sub S1 bar, S2 bar, S3 bar, S4 bar is equal to 1. Okay, so so Y over S1 bar SL is 1 if the opt partitions S, which is like the union to exactly so that's my intended meaning. Okay, so then yeah, just to get some inclusion. Yeah, then yeah, let's look at the set of like 2 variables. Okay, so then yeah, Y. So then yeah, let's look at U and V. What can happen between U and V? There are like only 2 possibilities. Okay, so they are Y, U, V. Okay, so they are the same, or they are separate. Okay, so there are like only 2 cases. Then yeah, okay, so then yeah, one can actually see that okay, so some of them should be like 1. Okay, so if you have like 3 variables, then I think that there are like 5 possibilities. Okay, so U, V, W, they're like all together. U is separate from the other 2 guys. Like then 3 of them, and then the U bar V bar. Okay, so yeah, when we have 3, then there are like 5 things. That's my intended meaning of these variables. Okay, so yeah, okay, so then yeah, okay, so then in order to formally at least capture some of these aspects, so then yeah, what kind of constraint should I put? Okay, so the constraint I put is also kind of very natural. Okay, so suppose that I know the value of y sub s1 bar, s2 bar, s3 bar, s4. Suppose that someone told me this value. And then I'm looking at this like set T, including S. And then now I'm curious what's happening with T. Okay, so I mean I still don't have a full information. So I don't exactly know what's going on with T. But then once I know that once I know the value of the y s1, s2, s3, s4, then I at least know that this whatever is happening with T should be consistent with my information with S. Yeah. Is there like? Okay, so then constraint that we're going to write down is that for any S1 through SL, again disjoint, and their unit size is 4. And then for any like T, containing the union over these guys. Okay, so then I know suppose that I know the value of y s1 bar through SL. Okay, so then that's my information for S. But then I know that okay, so that should be consistent with what's happening in T. Okay, so then it's going to be big summation. So then basically we are summing over all the partitions of T that is consistent with S1 through SL. Okay, so let me not write down the full thing, but then basically the T1 through T plus like even L prime.
Yeah, because you can.
Because it might be
it's a.
So okay, so partition, they partition T as a partition T. And then of course after reordering, as you said, you can demand that SI is contained in TI. No, I think
T is sigma I because there is some reordering.
I think so because this thing is symmetric, so perhaps like this is correct thing to write. Okay, so this is very like natural consistency constraint that I can write. And then perhaps like from the base case, I'm gonna say that YV is equal to 1 for every and then perhaps Y is between 0 and 1. Okay, so that's that's the whole relaxation for this problem. Okay, so then one can see that so this is kind of strengthening of this guy because once you have this like y uv and then y u bar v, then one can say actually so this is exactly x uv that we were talking about, the probability that the u and v are separate. Actually, it looks like I can only finish this part because I can't for the MBD part. Sorry about that. But then let me at least like finish this guy. Okay, so then is our relaxation clear? Good. Okay, so then let me say a few words about how we use this kind of power equivalence to go beyond this like the bottleneck. Okay, so then let's start from this the claim 2.5. Okay, so let's try to see like whether we can go beyond this like 2.5, which is already done actually by carefully choosing F. But then let's do it in a more like different way. Okay, so then one can look at so we know this claim is tight. What is like tight example? Okay, so and there's like one very specific tight the triangle, which is nothing but this triangle. Okay, so it's the plus minus, and then the LP value is the 0.5 0.5. Okay, so that's yeah. Okay, so then if this is a triangle, then one can see what is a value of cost UVW and LP UVW. Okay, so then one can see that so one can quickly compute that if like V is a pivot, so then this guy will be violated if like U and W both go with V. So that's gonna be 1/4. And then for the other case, it's kind of simpler because so this will definitely be outside. So if W is pivot, then U will be outside of W. And then it all depends on like whether like V goes with W or not. So that's gonna be half. It's 1.25. Okay, so then then the LP, so I'm not gonna bore you with the calculation. So one can check that this is the half. If that's where the gap of 2.5 comes from. But then one can kind of see that there's like some stupidity going on in the tightness of this claim. Because if you look at let's look at this term here. So that's exactly when the V is pivot. Okay, so V is pivot. And then LP thinks that U and W are like totally separate. Their distance is 1. One should never put U and W in the same cluster. But then this like the 1/4 is coming from the independence. I mean distance is half, like we're doing things independently, so that we probably 1/4. There might be in the same cluster, and then we are paying this unfortunate 1, which is like totally inconsistent with what the LP says. Okay, so then basically what you're trying to say is that so then independent rounding was good. That's pretty good. But let's try to like go beyond this. Okay, so then that's revise this LP rounding. Okay, so then so let's save some space by erasing this guy. Then so still we chose like P, and then we want to sample less given P. So then what are going to be the desirable properties? Okay, so the sample is a given P. Okay, so I mean we want to preserve marginals. In the sense that first one can what we want is that for every U, the probability that U goes with P is going to be probably exactly what LP value predicts. Okay, so perhaps like the Y PU, which is exactly the 1 minus X. Okay, so that's that is achieved by independent rounding. But then as a witness by this the stupid example. Like 2.5 example. So then we want to demand that now we care about this like what's happening between these like the two vertices, which is not P. So I want to kind of be sure the correlation of these two vertices, so that it's exactly matches what is projected by the LP. So then ideally, what I want to say is that for any like U and V, so the probability that S contains both U and V is exactly what LP value what LP thinks. Okay, so what's the LP value? So then it's going to be exactly Y sub P U V. It's exactly the probability that the LP thinks that the P U V are all together. Okay, so so that's on my requirement. Okay, so the question is question is can you sample such as given P? Okay, so then in this form, of course, actually we cannot. If such a thing possible, then we could have like solved the max cut exactly in polynomial time, which is like so P is equal to NP and things like this, or like we want to easily construct a counterexample. But then what one can say is that one can sample. Suppose that it's like property 1, property 2, such that, of course, like property 1 is satisfied. And then the property 2. Okay, so that we said we are going to satisfy approximately amortized sense. Okay, so then what one can do is okay. So for 2, so if you just take an expectation of UV over all pairs of vertices, and then if you look at probability, the difference between these guys. Okay, so it's gonna be at most the epsilon, which is 1 over root r. Yeah, so that's what we can do from regarding this like the preserving correlation between these two U and B. Okay, so this actually we kind of used it from this work of Raghavendra and Tan. Okay, so but then actually such a technique is known in the dense CSP literature for a while. So it's the precursors are Guruswamy year earlier, or like Swarak or Ravindra earlier. Okay, so and then one can see that if such a thing is possible, then one can immediately get like p-test for like a max cut or like any kind of CSP problem, because the crucial fact is that so we are expected error. Okay, so I just like read as an expectation, but then expected error is like it's gonna be like n squared times epsilon. Okay, so so if your instance is dense, then it's gonna immediately imply the p-test for CSPs. So then that's but anyway, so we use this lemma as a black box, and that's exactly probably the only place where we use this the power of the higher order Sherali-Adams. Just like dense CSP algorithms, they needed the higher order in order to sample something like this. Okay, so that's we have one more place. We needed like 4 rounds of Sherali-Adams, but then essentially that's the only place where we needed the higher rounds, higher R greater than 2. Okay, good. So then at least one can go back to this like the bad triangle. Which was like giving the ratio of 2.5. But then now, if you pretend that we had this like the perfect correlation sampling, then one can say that 1/4 is not going to be there, because like LP thinks that LP will report it that U and W are going to be totally separate, and then our rounding algorithm will respect that, at least some approximate amortized sense. Okay, so if you know that U and W are not going to be in the same cluster, then actually that's the half is gone. So then one can one can show that if we just do this, so then the ratio without then the ratio becomes like 2 instead of 2.5. Okay, so that's good. But then I say like 1.994. So how can I go beyond 2? So then let me be kind of very vague. So then the way we do is that basically what we show is that even so with the correlated rounding you get 2. But then even if you look at what's actually 2 is tight even for this triangle. But then we show that so this is the only triangle where it's tight. Okay, so it just and then so if you got if 2 is tight, then your triangle should really look like this. So then the question is like, can every triangle look like this. Okay, so yeah, and then the answer is no. I think there's again some kind of correlation going on. But then yeah, one kind of intuition is that okay. So then suppose that yeah, I'm looking at this vertex U. There's like this like triangle has like clearly there's on the kind of center vertex. There's an incident to like two plus edges. Okay, so then, yeah, then let's look at it's like plus neighbors. V1 through like Vk. Okay, so then yeah, then okay, so then can every the triangle incident on U be bad like this? Okay, so that's yeah, so bad like this. Yeah, but then the answer is again no, because yeah, so because if this guy is a bad triangle, so then it means that distance between these two guys is 1. And then if yeah, if this guy is a bad triangle, then yeah, V2 and V3 must be anti-correlated. Okay, so then V1 and V2 must be totally anti-correlated. V2 and V3 should be totally anti-correlated. Then again, yeah, then that alone implies that V1 and V3 should be totally correlated. Their like fate is always the same, which means that yeah, the U V1 V3, this guy cannot be bad triangle. Okay, so yeah, there's yeah, simple yeah. Okay, so then yeah, one can kind of at least like intuitively say that okay, so not every triangle can be bad triangle. So that's another place we need the power over Sherali-Adams into like the 4 or 5. Because like this depends on like looking at the 5 variables together. Okay, so yeah, that's why we can say that okay, so it's not the case that there are bad triangles happening everywhere. So there are yeah, and then we can do like some kind of averaging argument between those like bad triangles and non-bad triangles. And then that's how we slightly went below 2.
So for this, you are using the higher levels of the.
Yeah, so yeah, so in order to do this, then yeah, plus I need like 4 or 5 levels. Yeah.
Oh, okay. I was not seeing how you can see that with this.
Yeah, I know that. Yeah, I know that. Yeah,
You are
just,
using the higher level.
yeah. Yeah, and then yeah.
Would you use like a constant level to argue that there is not many? Like you.
Yeah, I mean, across this guy, I think yeah, 4 or 5 is fine. Yeah.
Oh, okay.
Yeah. And then yeah, one case yeah, this triangle is exactly that's exactly what's happening in the LP gap like yeah.
Mm-hmm. Yeah.
Good. Yeah. So that's that's it for correlation clustering. Just I hope you got some idea. I think there was like a lot of technicalities because like how to handle these errors. So in reality, yeah, what we are really doing is not just applying this correlated rounding for every vertex outside P. We kind of carefully choose like where we can do we can apply this correlated rounding lemma, and then for the rest of guys, I just do it independently. And then yeah, there are like some the engineering was going on, not very like fine engineering, very crude engineering, and that's why the number is like so bad. But then we didn't try to optimize the concept at all. So.
Oh, you mean the 1.94?
Yeah, 1.94. There's like this number is like total garbage. Yeah.
Okay, that was my question. If you know what's the round.
No. There's no science behind it. Yeah, for sure. Okay, so now
maybe I'll ask exactly this. But do you know what's the integrality gap of this beast, or have any feel?
No. I think that's a great question. So I think so.
It's annoying because there's levels. And then careful about what you mean by integrality gap. But
I mean, I think for like fixed R, you can ask okay, so what's the best integrality gap?
Yeah, but ideally you would like to say like something that you can let R go to infinity, but it goes to infinity faster.
Yeah, exactly. No, I think so question the only thing I know is that even when R is like 4, the only thing I know is like 1.001. Okay, good. So I have like 20 minutes left. Then let me. Then okay. Good. Any final questions about correlation clustering?
Maybe I have a general question. Have you tried anything along the lines of sum of squares, because that is sort of.
Yeah, exactly. So actually, one kind of nice question about so one kind of open question is that so this this is the gap the LP is 2, standard LP. But then yeah, one can kind of write down the standard STP. So that guy might have a gap lower than 2. At least like this one, yeah, this is not a gap for STP. And then it might be the case that standard STP might gap.
At the very least, you could try to run SOS and say, well, SOS gives me positive send definite for free, so that allows me to sample like a portion.
Yeah. Yeah, I think let's see. I think yeah. So this like sampling lemma and then dependence on R is tight. Somebody showed that, but then perhaps like tight only with respect to the Sherali-Adams. I don't know whether they show tightness. Yeah. So I think yeah. So yeah, I think so there, it's a totally consolidated SOS like does much better than SA. But then I think yeah, the only thing is that we don't know like the tools that differentiate these two.
In this problem, you have an underlying complete graph structure and only plus minus signs.
Yeah.
But if you have something sparser or
yeah, good. Yeah. So okay. So yeah. So of course, like there are like many versions. I think so. I think one kind of natural generalization is like what happens like if graph is not necessarily a complete graph. There are like some empty edges. So then yeah, then I think one can kind of easily see that this problem is equivalent to like this the multi-cut problem on a general graph. And then yeah, so that guy is a log and approximation algorithm, which is believed to be tight. It is like the unique games are to get any concept back to approximation. So I think yeah, that one kind of was observed very quickly right after the original formulation. And then there's another version which is like trying to maximize the number of agreements. Instead of minimizing the disagreements. I think yeah, those guys yeah. So I think in a complete graph, it's again p-test is achievable. And then in general graphs, I think there's it's really like looks like max cut. So yeah, using STP one can get 75% approximation errors. So kind of all kind of possible variants were studied. But then somehow I think this guy is is the most well studied guy.
what about the number of partitions? If you try to, I don't know, bound K.
Oh, that's a very good question. That's a very good question. Yeah. So if you say the K is bounded, number of parts is bounded, then there's a p-test, even for the minimization version. Okay, good. Yeah, so that's about correlation constraint. Yeah, so I can end it, or like if you guys want to hear a bit more about it, I can tell you a bit about the other algorithm, MVD.
You can go a little bit over time.
Okay. Okay, so then yeah, let's what I'm gonna do. So then yeah, let me try to like okay, so then let's switch let's go back to correlation clustering, and then let's go back to like the combinatorial algorithm that we raised. Okay, so and then yeah, I'm gonna tell you a bit about how to say it's a 3 approximation, and then I'm gonna tell you what our algorithm is for MVD, and then probably we're gonna stop there. Okay, so it's not gonna be end to that. So let's start from here. So then all this like correlation thing is gone. Then yeah, as usual, so now we are back to combinatorial algorithm. S is just like cross numbers. Okay, so then yeah, we want to say that okay, this algorithm is like 3 approximation. Okay, so then yeah, how do we say this? Okay, so then yeah, this is our algorithm is a purely combinatorial, but then the analysis is kind of LP based, but then the kind of different LP based. Okay, so we are going back to like hitting set interpretation, and then you're gonna write down this like natural LP relaxation for a hitting set. Okay, so then yeah, what we're gonna do. Okay, so then suppose that, yeah, let's say like script C is a set of all bad cycles. Okay, so bad cycles are defined a long time ago here. And then, yeah, sometimes we only want to look at the bad triangles. Okay, so then, yes, let's say script T, the set of the triangles. Okay, so then, yeah, yeah, as you said. Okay, so then what's going to be kind of reasonable output relaxation for this problem? Okay, as you said, it's okay. We can interpret this as a Hilling set. Okay, so then, yeah, we want to minimize summation of XE. Such that now XE indicates whether we modify this edge or not just the distance. Such that, yeah, for any like of the bad cycles P, so we pick at least one edge. So that's a very unnatural heating term relaxation. Okay, so then, yeah, it's a relaxation. We know that its values are at most optimal value. But then, the actual LP that we're going to compare it to is even weaker LP, where we are not hitting all the bad cycles, but then we are only hitting like bad triangles. I mean, okay, so it's a stupid LP. It might be really stupid, but at least it's a relaxation. Yeah, the optimal solution will hit every bad cycle for sure. Okay, so that's the LP that we're looking at. Okay, so then, yeah, what's dual? Just like the stupid covering problem. So then, yeah, then dual is gonna be okay. So I have a variable for each triangle, the bad triangle, such that for every edge, if we look at some of all the triangles contain bad triangles contain E, the alpha T value should be almost 1. So that, yeah, that's the dual. And then then the optimal value of this guy is at most out. And then we are looking at this particular LP, the packing bad triangles. Okay, so then let's try to analyze this guy. I think now, yeah, it can be done in 5 lines. Okay, so then what are we saying? Okay, so let's define this the quantity as usual. Suppose like that. So then let's say do the same thing. P sub U PW. Okay, so now, yeah, so perhaps like the only difference from the previous thing is that, okay, now we are looking at all the iterations at once. Okay, so yeah, over all iterations. So then, yeah, so what's gonna be the probability that the VW is a viable when U is given? Okay, so yeah, again, yeah, over all iterations. Okay, but then okay, so then let's look at the UVW again, and then see like when, yeah, what kind of triangles will allow this to happen. Okay, so then, yeah, let's look at UVW. And then there are like the 8 possible sign patterns. But then, yeah, one can see that if things are like this, okay, so which is kind of consistent, which is not a bad triangle. Not a bad triangle. And then, yeah, one can see that if this guy is not a bad triangle, then whatever your pivot is, it's not going to violate the other edge. Yeah, if a B is a pivot, then yeah, U and W will be separate, which is consistent. If a U is a pivot, then the V and W will be outside, which is fine. Okay, so then, yeah, so then outside of this, out of this like 8 sign patterns, there's only like one kind of bad triangle, which is this.
It's the same thing. Okay.
Yeah. So I mean, of course, this is a bad triangle. And then in this case, actually, yeah, so then it's conceivable that if you pick this guy as a pivot, then it's gonna be violated. Yeah, this guy's a pivot, this guy's violated, and things like that. So then then our like first observation is that okay, so in the beginning, let's look at triangle. Okay, so there are like 8 possible sign patterns. But then if the triangle is not bad in the beginning, then it's gonna be 0 always. Because like we're not changing the sign. I think at least in this interpretation, so we're just like moving down the verses. Signs will remain the same, but then if it's a good triangle, nothing's gonna happen. Okay, so then then it means that we only need to focus at the bad triangle here. Okay, so that's first very like simple observation. Okay, so then it's so this the quantity is defined as like this. Then one can see that. I mean, let's just like amortize our triangles first. So then as usual, P U V W is the summation of these 3 things. Then we know that expected value of the cost, let's say cost, the total cost is exactly summation of P, the P. Okay, that's good. And then my goal is to so then so I want to compare this guy to this program. Okay, so then I'm gonna do simply I'm gonna let the alpha t. So t is like bad triangle, and then we only have non-zero guy for the bad triangle. Okay, so then I'm gonna let just alpha t be just p of t. That's my probably divided by 3. And then I want to show that okay, so this solution is is a feasible dual to that program. And then once I do this, then we know that summation of alpha t is exactly the cost divided by 3. So then I prove that cost divided by 3 is a valid dual feasible value, which is at most the optimal value. Okay, so then the only thing I need to show is that the alpha t defined in this way is a dual feasible, which can satisfy this constraint.
So just a quick question: what happened with the pair thing? Because on the other one you had to sum the pair P U V because of when.
Yeah, I think I'm slipping something under the rock. Okay, let's hope that it's under.
It is there.
Yeah, I think probably it's gonna be the yeah. I think it's you're right. Okay, so then that's all I need to show. But then actually here's like very like subtle but then crucial observation. Okay, so I defined the P U V W this way. And then I said, okay, so it's going to be a summation of these 3 things. But then are these like 3 terms going to be different? Any different? So I mean, at some point it's kind of crazy because like, okay, so there are like crazy dependencies, But then what we are saying is that anyway, whenever like U, V, W are present in the current graph, then we are choosing the pivot uniformly. So the UVW will be a pivot with the equal probability. Of course, like this like whatever situation, that contains UVW, it might be crazy. But then whenever UVW are an option, they will become the pivot with the same probability. Okay, so then actually one can say that those 3 guys are indeed exactly the same. And that's the craziest part. So yeah, do you buy this or it's
Also, you're also using that it's the triangle looks like that, right?
I'm using
The probabilities are the same, but also each of the contributions are also the same.
and then also if like one vertex is gone, then this like any of these three objects will ever.
Gives you exactly
Yeah.
one, I guess.
The thing. Okay, so then if you buy this, so then then why should this inequality be satisfied? Okay, so then let's look at the one edge UV. Okay, so then at least we know that. Okay, so then let's if you sum over every other like W, the P sub W over UV. Okay, so that's you know that that's at most 2 months. Because this is exactly the probability that UV is violated. Given W. And then the crucial observation, which is not going to be true in MVD, is that once UV is violated, then it's going to be gone forever. I mean, if a UV is on the plus edge and it's violated, means it's cut, so the edge will disappear. If a UV is on the plus edge and minus edge and it's violated, then it's going to be contained in the new cluster, so it's going to be gone anyway. Okay, so that's why this thing is true. Okay, so it can be violated at most once. Okay, but then by this thing, okay, by this equality. Okay, so then basically what you're saying is okay, then basically we are summing over all the bad triangles containing UW, and then P sub WUV is exactly the P over T divided by T, because they're all the same. And then so that's and then alpha T is exactly PT divided by 3. So alpha is a dual feasible, which proves that it's through approximation.
I got a little bit lost. Why is the sum over WUV?
Exactly. So good. So so this is the probability that VW is violated, given W is a pivot. So then basically it is saying that UV is violated at most once. The probability that
it's violated at most once along the algorithm, not at a certain stage, right? Because
actually, this probably is with respect to all the stages. So we are considering all the stages at once. It's kind of different from the previous one. It's like all these over all iterations.
So maybe tell me what's the definition again? The probability is the probability that VW is violated given that U is picked at some stage.
You picked some stage as a pivot. So so U is a guy who violated VW. U is a pivot who violated VW at any stage. I think that's the definition. That's why. That's what makes this thing kind of more like mysterious. Like it's over all iterations and things like this.
I agree with the last vehicle, but now I need to think about the others.
I think exactly. So but then it is what it is actually. It's like 5 lines, and then it proves that it's a 3 approximation, which is pretty cool. Okay, so but then so then I'm gonna end soon. But then before doing this, then at least let me state the algorithm for MVD. Okay, so just it's just almost the same thing, but then it's slightly different. So we are not removing stuff. So we will iteratively fix out some distances. Okay, so then suppose that we start from our original distance vector x. Okay, so now let's do MVD. Okay, so while So X is not metric. Okay, so then we choose P uniformly random. Okay, so then what we're gonna do is that we kind of fix all the bad triangles containing P. Okay, so then what we're gonna do is okay, so P, so at least like when we choose P, then I will consider all the distances incident on P as like fixed. Okay, so that probably they're gonna be good. But then if you believe this, so then there are some like bad triangles involved in P that will appear. Okay, so then basically what we are doing is that for any the I and J, such that so probably the first case the Xij is like 2 great. So Xij is greater than XPI plus XPJ. Okay, so that's one possibility. So there's a bad triangle involving P. So then okay, so I want to minimally change this. Though actually I don't pay for numbers. I only pay for like modification. But then still I'm gonna let Xij just minimal change. Summation between these two. Okay, so then and then another case is Xij is like too small. Perhaps Xij is less than then again like minimally change. That's the whole algorithm. Okay, so so but then your first question is like okay, so is it even ending? Because like it's like it looks like very local. Okay, so all you do is okay, there are like some bad triangles. I mean we are maintaining X. So if there's no bad triangle, we're gonna be done. But then of course like we're kind of like trying to fix like these like bad triangles very like myopically. Just choose out P and then only fix the bad triangles containing P. Yeah, but then it's like not very like complicated. Just like some case analysis will show that okay, so if you look at the set of all like bad triangles in the beginning, okay, so by doing this process, it will only decrease. Okay, so we are changing the distances of Xij's, but then it will never be the case that the bad triangle is created from like not being bad. So that's never gonna happen. So that's one thing. And then so then at least like then we kind of know that okay, so then this algorithm will terminate and give you like some feasible solution. That's for sure. And then in order to analyze it, so we are basically following the same framework. Okay, so that then now it's okay, so this is like the finally becomes modified. And then basically in this case, what we are showing is that this quantity 1 perhaps becomes an order log n. Okay, so again, so based on some again, everything's very simple. Then the simple observation, and then that's what gives us log n approximation. So I didn't do much things, but then that's the full algorithm. So kind of very simple, and then that's that's a full analysis if you believe this this level. Okay, so I think so regarding MVD, I think the most the outstanding open problem is like it is closing to figure out what the approximation factor is. I think the best lower bound is 2 from vertex cover log n. So still like it might be the case that it has a constant factor or not. So it's and then generally in this space and then there are like some other special cases. Because like okay, so we handle this general metric and then correlation goes to a very specific metric, 0-1 distance metric. But then one can question like pick your favorite metric, L2 or L2 in bounded dimension, whatever. Okay, so then can you do the same thing? Okay, and then some of them, we studied this, some of them, and the other people studied this as well. So I think one thing that is actively studied is the ultra metric. Because like the tree, the metric coming from this hierarchical tree. So that guy, one can show that one can have a constant vector approximation using kind of different method. But then so that's some that's generally the space of the things that people are still thinking about some metrics. But then I want to also say some observations, because like going back to the CSP world, one can kind of so we kind of at least like some part of our algorithm, our like algorithm is like heavily inspired by this CSP connection, just like CSP on a complete graph, just like the alphabet is kind of weird metric space. Yeah, so and then one thing is that one can even like kind of interpret like more problems in this like CSP language. I think one kind of the connection that I like is a low rank approximation. Yeah, given the n by n matrix and then number k, find me the best k rank k matrix that differs from the given matrix in the least number of entries. Okay, so then in that case, one can view it as a CSP, where like there's like a variable for each row and column, and then they are like they can take a value, just like which is like vector in the k dimension. And then if you fix out the value for row and column, then that's going to induce the inner product, and then we're going to get penalized if that inner product is different from the given matrix. Okay, so we have some follow work actually solving that problem. Again, like viewing this problem as a CSP. So I feel that a lot of these like distance related problems or like matrix related problems, they can be interpreted as like some instance of a CSP, because like the matrix is nothing but just the complete bipartite graph. And then so are distances. Okay, so I just want to say that it's there are more connections that can be made between these like the problems and then CSPs and even like kitting sets. So that's it. Thank you.
Do you have any guesses for the CC constant? Is there some kind of natural, like 2 was before a natural lower bound?
That's a good question. I don't have 1.5. I have 50-50.
Okay. But there is 1.5 is for some reason a natural point where like this approach you were describing breaks. Or?
No. I think just 1.5 is like
The natural point is wherever is the.
So I'm asking what is that 1.4? What's the?
That's I don't have a guess right now. And actually, another like interesting that might be interesting question is whether like this dependence on n is necessary. Means for now we are saying that okay, so in order to get the 1.99 whatever factor, somehow your running time should increase. Exponent of n should increase. So then but then 2.506 that's just a simple n cube or like n square algorithm. Okay, so he said then one nice question is that if you want to go below 2, so then can you do it in a linear time or a quadratic time? It's a kind of more like fine-grained complexity approximation, fine-grained approximability setting. So that one might be able to prove that.
You mentioned this rank A approximation, right? And you view it as a CSP. How much do you pay in terms of running time with K?
So I think so we got something then we are paying. I mean I think we are treating K as a purely as constant. So I think perhaps like it's gonna be like double exponential in K, something like this. I think actually so I think low rank approximation regarding that I think there's like some previous work. I think but then they were kind of studying kind of different objective. Of course, like if you're error measured for uniform, that's can be easy. You can do it exactly using SVD. And then people studied L1, just like the entry as L1 differences, things like this. I think and then there are like p-tests and then all of them have like n to the k or like some like a function of exponential is k is needed. I think otherwise there's some hardness. If k is general, then you can't to get p-test or even super constant approximation.
More questions?
Yes, most of the questions during the talk.